Hello, welcome back to the course of maintenance. Today we have a fresh new topic, the topic of machine learning, and the lecture includes an introduction to machine learning, as well as an overview of unsupervised learning. Overall, we will try to answer the question of how does unsupervised learning works, and essentially how do we work with data where we don't have the labels, we don't know the meaning of the data and what do we actually want to predict. And that is all about unsupervised learning. As usual, we have a very busy agenda, and this time we have 6 topics to cover, ranging from the introduction to machine learning, passing through the focus topic of unsupervised learning, and detailing the methods of clustering, which is an approach inside unsupervised learning. So we will talk about KMeans, hierarchical clustering, DBScan, and also the self-organizing map. So stay with us, and thank you for watching. I am one of those persons that really likes Trivial Pursuit and answering questions, trying to guess things. And there are things that are harder to guess than others. So there are questions that are more difficult to answer than others. And in machine learning, we have many different questions that are difficult to answer. Such as, for instance, what is machine learning? Examples of machine learning, what are those? What is the difference between machine learning and artificial intelligence? And what is the difference between machine learning and deep learning? And what is deep learning anyway? All of these questions make us want to study more about machine learning and understand more what is implied in machine learning. And we will try to answer some of these questions. In the last decades, we have witnessed the increasing importance of the fields of artificial intelligence, of machine learning, and deep learning. All of these fields try to derive insights from data. And that is really important. That has provided a great progress in many applicational fields. Let us see some examples. I could talk on for hours about all the developments that have happened in the last decade regarding artificial intelligence and machine learning. As examples, we have the Tesla car and the autopilot system. We also have the DALL-E system, which is a system that allows you to generate images according to descriptions. We have advanced fire protection systems based on computer vision and deep learning. And we also have in healthcare the diagnostics being more and more assisted by advanced algorithms based on machine learning. All of these are examples of how we have progressed in terms of technology and in terms of machine learning and artificial intelligence in the last decades. Have you ever thought about the difference between the terms of artificial intelligence, machine learning, and deep learning? Well, they are different, but they are interrelated. Because, for instance, artificial intelligence is a major field that encloses machine learning, that in turn encloses deep learning. But what is artificial intelligence? It is essentially the simulation of human intelligence. Machine learning, in turn, refers to the ability of machines, of computers, to learn without being explicitly programmed to do so. And deep learning is nothing more than machine learning that focus on neural networks with more than one layer so that they have a certain complexity to it. When I was young, I was in a course of artificial intelligence. In that course, I learned many things, but I did not learn about machine learning. At the time, we wouldn't talk much about neural networks or random forests or those algorithms. We would focus instead in artificial intelligence algorithms, such as searching for values in arrays or searching for values, for example, in a tree of values. And those were the things that we would learn. And that is artificial intelligence, but that is not machine learning. What's the difference? The difference is that in general, artificial intelligence is any algorithm that tries to simulate the intelligence of a human, and a tree search can be a good candidate for that. However, machine learning is about learning from the data and without being explicitly told what to do. A tree search algorithm will have to be explicitly programmed to do so. And that is fundamentally the difference. You probably have heard the expression learning from examples associated to machine learning. So what do we mean when we say that a machine learning algorithm learns from examples? We are saying that they do not learn explicitly. They will learn by looking at the relationships in the data. And that's kind of like the way that we, in the majority of the cases, learn, especially the children. So whenever we're learning how to talk, we hear all of these words, all of these examples, and one day we compose our own words based on our experience. And that's the same for a machine learning algorithm. It tries to learn not explicitly from a code or from a set of rules, but from looking at the data and trying to explore the relationships in the data. There is this famous dish in the Netherlands that is the stampot. And imagine that I want to have an algorithm, a machine learning algorithm that identifies stampots in images, in pictures, in photos. What do I have to do to train my algorithm, to make it learn? First, I will have to gather a lot of pictures of food. So, some of these pictures will be about stampots, some of these pictures will be about different foods, but I have to gather a lot of information because you can learn from examples, of course, but you need a lot of data. Once you have this data, you can receive new data, but you will not gather that data. You will just classify it. So you will receive a picture with a stampot, and you will say, this is a stampot, and I have the certainty of 90%. Then you can receive a picture of a non-stampot, and you can say, this is a stampot with a certainty of 40%. You made the wrong guess, but it doesn't matter because in most cases, hopefully, you will guess correctly. But the idea is that according to the image that you receive, you will make a decision if it's a stampot or not, based on the examples that you have in your database and based on the similarity calculations that you make. Have you ever heard about the expression, I did a regression classifier? Or have you ever heard someone say, I did a supervised learning model? I'm not sure if you ever heard about these expressions, but we will try to explain them. So there's this huge field that is machine learning, and it has inside two classes of learning, the supervised learning and the unsupervised learning. Within the supervised learning, you have classification and you have regression. But what is the distinction between supervised and unsupervised learning? The idea is that you have extra information about what you want to predict or classify in the supervised learning world. So for example, going back to the stem pot example, in that situation, you have the labels, because for each picture, you can classify it as a stem pot or not stem pot. You know if there's a stem pot or not in the pictures. I know it's a tedious task to classify all of those images that is in your training set, but you can do it. So you can do supervised learning. In other situations, you don't know the meaning of the data. You don't know the true classification. And in that case, you have a harder and more difficult task to do that's enclosed in the field of unsupervised learning. It is important to establish the difference between supervised and unsupervised. In unsupervised learning, we have a set of data points, such as these ones. In this case, you only know that they are defined by two dimensions, dimension x and dimension y. But you don't know anything else. You don't know the true labels. If the 4 points at the top left is a group or not. It looks like one, but you don't really know. You don't have access to that information. So you can apply a K-means and you can identify different groups, but you will never know for sure if your grouping is well done or not. In supervised learning, the idea is that you know for your set of points the class that they belong to. So if you look at the past, you will try to establish a boundary between the classes. For example, if you have two classes, you will establish a boundary between the green points and the red points. And when new data comes, you will use that boundary to classify if the point is green or if the point is red. You may have a good guess or a bad guess, but importantly, you always know the true value of a data point. So you can know if you did a wrong guess or a good guess. So you can calculate the accuracy and the performance of your model. In this lecture, we will focus mostly on talking about unsupervised learning, so let us forget the supervised learning until the next lecture. And curiously, many people think that unsupervised learning is only about clustering, but that's not entirely true. You have other methods such as the association rules and the dimensionality reduction, all interesting methods that we will skip for now in this lecture, and we will focus mostly on clustering. And why? Because these are perhaps the most complex, the most used, and the most representative method of unsupervised learning. So we talked about artificial intelligence, then machine learning, then supervised and unsupervised learning. Within unsupervised, we have clustering, this beautiful set of algorithms. And what is it? Well, it's a set of techniques or methods whose goal is to find similarity groups in the data, is to find clusters. These groups that we find that have data points that are similar, we call the clusters. And when we do clustering, we have two goals, always, in any kind of clustering. The first goal is to maximize the similarity of the points that are within the groups that we form. The second goal is to minimize the similarity between the groups. And that is essentially the idea of clustering. Because the clustering is always grounded on the notion of similarity, we need a similarity or distance function in all our clustering algorithms. And a distance function or a similarity function needs to respect essentially four properties. The property of symmetry, which tells you that the distance from from going from A to B is the same as going from B to A, the property of the constancy of self-similarity, so the distance from A to A has to be equal to 0, and the property of separation or positivity, that tells me that if the distance is 0 from A to B, then B has to be equal to A. Perhaps the most complex property is the triangular inequality property, that tells me that to be a distance function, the distance from A to B, considering an extra point C in whatever part of the map, is less or equal to the distance from A to that point C plus the distance from B to that point C. But you may ask me, okay, but what are the distance functions concretely? Can you give examples? Well, I can. The most commonly used distance functions are, for example, the famous Euclidean distance, the Manhattan or city block distance, and the weighted Euclidean distance. The Euclidean distance is basically the shortest path between 2 points, while the Manhattan distance goes around the block to reach the location. That's why it's called the city block. The weighted Euclidean distance is a little similar to the Euclidean distance, but it puts weights on the dimensions. And if you add up all the weights, they add up to 1, of course. And the idea is that, for example, a certain dimension may be more important than the others to calculate the similarity of one point to the other. But this wouldn't be complete if I didn't show some equations. And how do we calculate the Euclidean distance, the Manhattan distance, and the weighted Euclidean distance? The idea is that you should have 2 points, so you always calculate the distance between 2 points, and the points have dimensions, so they are arrays of dimensions, values, and you compare those values and try to come up with a number that makes sense in the end. Importantly, in the weighted Euclidean distance, you have the concept of weights, so you assign some weights to each dimension. To conclude this section, I would like just to give a summary of what we have been talking. So what is the recipe to perform clustering? You need a clustering algorithm, you need a distance function, you need to target 2 goals. The goals of intercluster distance has to be maximized, and the intracluster distance has to be minimized. Overall, the clustering will have a certain quality that depends not only on the algorithm, but also on the distance function that you choose and on the application. So you can have an algorithm that works very well for an application, but not so well in another application, even with the same configuration. It is now time to look into the algorithms of clustering in more detail, and we will start by the KMeans algorithm. There's many things that we can say about the KMeans clustering, but perhaps the 2 most important is that it's an algorithm that's iterative, so it involves several cycles until the end, until you get the clustering. And the other thing is that you need to set the K. That's why it's called KMeans. So you need to set the K, and the K is the number of clusters that you will search for in the data. Having to select the K is to a certain extent an advantage if you know the number of groups that you're searching for, but it's a disadvantage if you don't know or you are unsure of how many groups of data you have in your dataset. But how does the K-means clustering works? Well, it works in 3 steps. The initialization, where you pick k random data points as cluster centers, regardless if they are good centers or not. And the second step is a cycle. In each cycle, you do 2 things. The first one is to assign data points to the closest cluster center. After you assign the data points, this doesn't mean that the clusters will have its center at the cluster center. So you have to update the cluster center to the average of the assigned points. And you do this many times, and the third step is to stop when no point assignments change. So we have here more equations to scare us all. Just kidding. But the idea is that in the K-means clustering, we are trying to minimize the distance between the points and the center of the cluster that we choose for those points. That's what this first equation means. And then we have the other 2 equations of the cycle, where you fix the centers and you're trying to optimize the cluster. So you're trying to assign points to the clusters based on the minimal distance between the centers of the clusters and the points. After you fix the clusters, you can optimize the new centers, and you do that by taking the average of the points that you have found for that cluster. Let us see this in more detail with an example. And in this example, we have 8 points, each with 2 dimensions, and we see the x and the y dimension here. In this example, for the clustering of K-means, we will use the Euclidean distance. This is the most popular and common option for the K-means, and it calculates, using this equation, the shortest distance, the shortest path between 2 points. To help us make our calculations, I will create a distance matrix where I will put in the first column all the points, the name of all the points, and as the first row, all the points also. So each cell will indicate that I'm going, for example, from A1 to A1, or from A2 to A3, and so on. Since the matrix is symmetric, I will only consider part of the matrix. After calculating these distances, I can select 3 points, because I'm going to do 3 clusters, to be the centers of my clusters. And now I'm going to perform the first step of the first iteration. So I will do this for all the points, and I'm going to try to assign them to the best cluster possible given the centers that we have just selected. So for point A1, I will calculate the distance from the seed of 1, which equals A1, from the seed of 2, equals A4, and from the seed of 3, which equals A7. And as you can see, because the distance of A to A is equals to 0, the distance of A1 to A1 equals to 0 also. So A1 will belong to cluster 1. In regards to A2, I will calculate the distance of A2 to the different cluster centers. So for cluster 1, I'll go for 5. For cluster 2, I'll go for 4. For cluster 3, I'll go for 3. So A2 will belong to cluster 3. And this is the result of the first step. We have for cluster 1 a single point. Cluster 2 is composed of several points. And we have cluster 3 with only 2 points. But as you will notice, the centers of all the points that we have selected for a cluster do not coincide with the cluster center that we have calculated previously. So what we need to do is to update the centers. So we recalculate the centers. Each center point will be the average of the data points that are associated to that center. In our example, the centers will change quite a bit. In cluster 1, the center will be the same because it's composed only of one point, but in cluster 2, it will shift downwards. And the opposite behavior will happen in cluster 3, which will shift upwards. After several iterations, we will reach a point where the system is stable, the clustering is stable. And in our case, we end up with 3 clusters where the first cluster will have 3 points, the second cluster will also have 3 points, and the last cluster, the third cluster, will have 2 points. The KMeans is very popular and common algorithm, but it has its limitations. One of its major limitations is that we are required to set the K. So we need to set the number of groups, even if we never or we are unaware of the groupings, the possible groupings of the data. The other limitation has to do with the fact that according to how you initialize the centers of the clusters in the initialization step, you may end up with different end solutions. And this makes the algorithm a little bit unstable to that extent. Another characteristic of the K-means is that it tends to work very well when the clusters are sphericals, but when the clusters have a different shape, because it's trying to use the Euclidean distance in search for spherical clusters, it doesn't work that well. It is also the case that if you have outliers in your data, the clusters may be transformed to something that you might not want in the first place. So instead of creating clusters around the outliers, the K-means will elongate or change the shape of other groups of data points. Let me just leave a brief note on the hierarchical clustering before we study the DBScan and the self-organizing map. In most cases, we use partitional clustering algorithms, where we have the data points in a certain space, like a 2-dimensional space, and we construct a partition of the 2-dimensional space, and over time we evaluate the partition, and eventually we change the partition until we are more or less happy with our results. Hierarchical algorithms are different because they pick the data and they create a hierarchical decomposition using some set of criteria. Hierarchical algorithms can be of 2 kinds, agglomerative, which are bottom-up, or divisive, which are top-down. They both can reach the same outcome, but they do it differently. So in the agglomerative method, you go from the data points until the major root group, and in the divisive method, you go from the root group until the leaf groups with the data points, the singular data points. Now let us talk a little bit about the DBScan and how to do density clustering. There are many clustering algorithms based on the concept of density. One of these is the DBScan that we will talk in this section in much detail. But be aware that there are others, such as the DENCLU or the optics, also very well known, or the click. All of these algorithms are based on the basic concept of density, and DBScan in particular sees density as the number of points within a given circle around a certain location. And he uses density to identify if a given data point is a core point, a noise point, or a border point. In DBScan, you classify a point as a core point if within a certain radius that you have to define, there are more than a certain number of points that you also need to define. So you need these two parameters in DBScan, the radius and the minimum points that define the density of a core point, the minimum density of a core point. The other two types of points, the border point and the noise point, have to do with the proximity to the core point. So a border point is not a core point, of course, but it's in the neighborhood of a core point, while the noise point also don't have a large density, and it's not close to a core point or to a border point. The idea is that the DBScan will look at a set of data points and will classify the data points as core points, border points, and noise points. And then it will look again and see how the data points are dispersed in terms of their classification and will detect the different clusters. DBScan has a lot of advantages compared to the KMeans. Of course, you have to define the two parameters, the radius and the density, the minimum density of the clusters. But apart from that, you don't need to set the K, the number of groups that you're trying to find. And this gives the algorithm a lot of freedom to handle clusters of different shapes and different sizes. It is also very robust to noise, so you can identify the noise points very easily. And it's also a fast algorithm. As everything in life, DBScan also has its limitations, such as, for instance, if you have data that has varying densities in terms of clusters, you will have a hard time trying to find those clusters with DBScan. DBScan also does not work very well with high-dimensional data, and that's also a limitation. We are now entering the beautiful world of the self-organizing map. The self-organizing map is a clustering method that is interesting to talk about because it is actually a neural network. So let's see how this works. Interestingly, neural networks are not just used for supervised learning, but they can also be used for unsupervised learning, such as, for example, the self-organizing map. In the self-organizing map, you have a two-dimensional grid, a two-dimensional space, and you give it data. And the data is multidimensional, and it's going to transform the data onto the two-dimensional grid. Importantly, the self-organizing map gives a way to show the data in a visual form, and it preserves the geometric relationships between the data points. The algorithm assumes that you have a two-dimensional grid and that each point of the grid is a neuron, and the neuron is defined by a weight vector, so a vector of weights. And you initialize those weights randomly. And at each time, you go through your data, through each data point of the data, and for each data point, you find the most similar neuron. You then adjust the winning neuron and its neighbors according to the data that you associate it with. And you iterate over and over again until you stabilize your relationships. I would like to thank you for staying with us until the end. I hope you have enjoyed the lecture. Machine learning is without a doubt a very important topic nowadays. I hope we have caught your eye to the importance of the field, especially for maintenance. It is very important because we use data-driven models very extensively in predictive maintenance. And thank you for watching, and see you next video.